Hey everyone, welcome back to the channel. So, in the previous video, we derived the velocity function with respect to x. And I also mentioned to you that this isn't part of the syllabus, but of course it's interesting to know. So now, what are we going to do today? Well, today, using this equation that we have derived, we're going to derive the x function. So I have derived it using differential equation in one of my videos, but that method is really long, but it's also one of the way to derive it, of course. But today, we're going to do a shorter way, but still using differential equation, of course, just a bit shorter. And we're going to still get the x function. So let's see how short this way is, okay? So without further ado, let's get started. Okay, so we know that this plus minus ideally means v is equals to omega square root a square minus x square, or v is equals to minus omega a square minus x square. So I'm going to derive using this one. You can also derive using this. Both equation is going to yield you an equation of x. So I'm going to do the one on the left hand side. Then you can try later on the right hand side and see if you can get an equation. Okay, so what are we looking at? What is our end product? So our end product is actually, if you remember, we have a few x function. It's actually a few, right? So I'm just going to give you, maybe one of it is x with respect to t is a sine omega t plus phase constant. So even this phase constant part, I've also mentioned in one of my simple harmonic motion video that it isn't really part of the syllabus, but you learn this in waves chapter in AS level. So yep, so I just thought, why not share with you, right? But yeah, so this is what we are expecting at the end. So let's see if we can get it by using the shorter way of differential equation. Okay, so let's start. Okay, let me pick a color. Okay, maybe a bright one. Okay, a bright one. So we know velocity is dx dt, right? So we can rewrite it as dx dt. Wait, let me write properly. Okay, dx. Wait, why did the color change? Okay, dx dt equals to omega sert a square minus x square. Okay. Now what I'm going to do is, I'm going to rearrange the variable. I'm going to arrange them, organize it. One side I'm going to have it as only x, and one side I'm going to have it as in terms of t only. So I'm going to put my left hand side is in terms of x. So dx is going to be here, dt is going to be here. So we know this entire thing is in terms of x. So what we can do, bring it over. So what will we get? We will get 1 divided by square root a square minus x square. Then the omega just stays here because it's a constant. Also, just to let you know, by constant, I mean constant throughout the oscillation. For example, for the oscillation of spring during the simple harmonic motion. Omega is not a universal constant like gravitation constant. No, it's not that. It's just constant throughout the oscillation. So for example, I have spring A. So spring A has this particular omega, and throughout its motion, as it oscillates, it will have the same omega. But if let's say I have spring B now, with let's say a higher spring constant, a higher k value, then in that case my omega would change. Right? Because omega is actually considered as angular frequency in your simple harmonic motion. Okay, so now let's get back to deriving. Okay, so after that, what do you do with this equation? You integrate both sides. Now, this is actually a very rare integration. I mean very rare function to integrate. And if I'm not mistaken, and I think I am not mistaken, that this is not in pure maths 3. This, like, for you to know how to integrate this is actually part of further maths. But if you are also curious, no problem, you just open your MF19, your formula booklet, just flip the formula booklet, go all the way to further pure maths and go to the integration part. You will see a function like this. So in the integration part in the formula booklet, it's 1 divided by the small letter a square minus x square, and when you integrate that, they told you you're supposed to get sine, the color changed again, sine inverse x over a. In this case, ours is capital A because we are using the capital A here, right? Equals to omega t, because we are integrating, not differentiating, sorry, integrating in respect to t, omega t plus phi. So this phi is actually a constant, like an arbitrary constant. Usually we put c, right? But in the end, you can also rename the c to be phi. But I'm just going to straight away put phi here. So this is actually the arbitrary constant. You can either do it on your left or on your right. Well, I'm used to doing on my right, so I'm going to plus it to my right. Don't do both sides, okay? Only plus one side. Okay, so since we have sine inverse on our left hand side, what we can do is we can bring it to the right hand side. Therefore, okay, when you bring a sine inverse to the left hand side, you'll get sine omega t plus phi, right? Okay, x divided by a equals to sine omega t plus phi. And now making x as your subject, you get x equals to a sine omega t plus phi. Seems familiar with this? Yep, it is definitely familiar. And it is also really short. Okay, how many steps? 1, 2, 3, 4, 5. Only 5 steps. The x function that we derived in my previous video, that has more than 5 steps, I believe so. So, yep. Interesting, right? That there's another way to actually derive it. So, this is about it. You know, there's not one way to derive. As usually, sometimes there's more than one way. And I find it really interesting to see that there is different ways to approach the same thing, but all leads you to the same answer. So it's just a matter of perspective, right? So amazing, we have derived 2 equations here. One is the velocity function and our x function. So that's all for today's video. I hope you learned something interesting today, and I'll see you in the next one. Bye bye and have a nice day ahead. See you!